Um, Before we introduce the speakers, there's a few announcements. So, well, the Yelp doesn't have anybody to make announcements, so I basically say a few words on their behalf. If you're looking for jobs at Yelp, so you can talk to Rebecca. She's sitting right back on near the windows. So talk to her about the opportunities at Yelp. Since I have the mic, so I'm going to say a few words on my company. So I work for GoPro. I'm the head of data science and engineering at GoPro. So I also have a few openings. So if you want to work for GoPro, you can talk to me afterwards. So so we have the two talks tonight. So the first one is Jeff. Jeff works for the company Heroku, and they're going to talk about how to push the limits of Kafka and go beyond 50,000 partitions and see. And this is Kafka has been used for many companies, and including GoPros ourselves. We're using Kafka as well. So when I hear the talk and the first time, I say, "Wow, this is I got to introduce this talk to our members." So with that, welcome, Jeff.
Sure. Thanks, Chester. Can you guys hear me okay? Okay, great. So hi, everyone. My name is Jeff Chow. I'm an engineer at Heroku. I work on the data team, but specifically, I work on the team that provides Apache Kafka as a service. So today, I'm going to be talking about how we've operationalized and pushed the limits of Kafka at scale, and how we've been running this service for our users for several years in production. But before getting too deep into it, let's first go over some of the core concepts and fundamentals of Kafka. So just a show of hands, how many of you guys use or have used Kafka in production before? Okay, good. So about half. So we'll kind of breeze through this at a reasonable rate. So Kafka today is many things. It's an API, it's a connector framework, it has streams, and it has a core messaging. It has like a core messaging functionality. But today we're just going to be talking about Kafka at its core, which is essentially just a distributed messaging system. So this distributed messaging system consists of 5 fundamental components, and they are brokers, topics and partitions, and producers and consumers. So brokers are just individual instances of Kafka or processes that manage streams of messages. These streams of messages are categorized into topics, and topics live on brokers and have generally 1 or more partitions. These partitions are simply just write-ahead logs that write messages in the order that they're received, and then has them stored directly onto disk. Now, I would like to point out that Kafka essentially thinks of partitions as its fundamental atomic unit, in that what I'm saying is essentially topics are just abstractions for groupings of partitions. So Kafka thinks purely in terms of partitions. Now, with that said, partitions are Kafka's fundamental building blocks for message ordering and parallelism. Now, if we surface back to the topics, these topics themselves are replicated onto other brokers. So in other words, there's extra copies of data living on ideally other brokers in the cluster. But topics, but specifically their partitions, are replicated individually to other brokers. On the client side, we have producers and consumers, and these guys just simply write to or read from topics. Now, getting a little bit deeper, these producers, although they write to topics, they write specifically to partitions, and it does so by putting messages through some hashing scheme, and then through this hashing scheme, it gets routed to specific partitions. And messages can either have a key or without a key. It really depends on however you want to write messages into Kafka. The consumer side is a lot more straightforward, where essentially you just assign which partitions that consumers should read from. But the neat thing here is that consumers maintain offsets for each partition. And this is a really neat mechanism because this allows consumers to not only process at their own speeds, but since they know their offsets, they can recover their progress from when a failure occurs. And the offsets basically just represent where each consumer has read up to within a partition. So if it failed, it knew that it was already at this point in the partition, then it can just resume back from that point. So aside from these fundamental components, there are many other moving pieces in Kafka, let alone things like streams and connect and API. There's lots of things to consider when you're talking about Kafka in the operational sense. Things like, how does Kafka achieve HA? And then how do you prevent abuse from misbehaving users? Things like quota management and security. And then there's more general things like system level stuff, like OS, JVM, and Kafka tuning, and then other even dependencies such as managing Zookeeper, which is a whole other talk. So going more general, you have to consider things like the underlying physical or virtual infrastructure, so things like networking, disk, monitoring metrics, and some sensible logging solution. And for Kafka itself, there's things like version upgrades, and how do you upgrade to Kafka? How do you upgrade Kafka versions, and what do you do when faced with breaking changes? And how do you roll that out to all clusters or all brokers in your entire fleet? Finally, there's things like maintenance, very, very general, such as what do you do when you have underlying server or disk corruption, and how do you even automate some sensible replacement strategy for that? It's a lot to think about. So Kafka is pretty flexible, but it has tons of operational complexities and burdens that you have to consider when trying to operate this thing at scale. But real quick, as a shameless plug, fortunately at Heroku, we do offer Apache Kafka as a fully managed service. Basically, it's your cluster, but we'll take care of all the operational burdens and complexities for you, so you can just move on and write some data pipelines or other data-intensive use cases. Again, we've been operating this infrastructure for several years in production now. And in production, we have hundreds of clusters. This is probably close to about 1,000 now. And the cool thing is that some of these clusters have thousands of partitions per broker. And we'll get more into that later. We've seen some of our users hit about 150 megabytes per second sustained for produced and consumed traffic. And this is about 5 milliseconds of latency on a message or less. In addition to that, we do operate these clusters in data centers around the world. So you can spin up clusters in US West, East, Europe, and Asia, et cetera. But more importantly, the Kafka brokers themselves and the Zookeeper nodes are striped across availability zones for fault tolerance. And to top that off, basically, we place these partitions in a rack-aware manner, so also across availability zones for the same guarantees. So getting to this point took a lot of work, and there were lots of things to deal with. Primarily, we were really interested in pushing the limits of Kafka, so that you could say we wanted to get ahead of any challenges that might come up, so that our users wouldn't have to face these challenges in production. Because, as a service provider, it's our job to make sure that our users are basically safe from these really odd corner cases, so that they can just get on and write their data pipelines and use cases. Because otherwise, the chances for shooting yourself in the foot are quite high when dealing with things Kafka. So what do? We set out to build tons of internal tooling and infrastructure, monitoring and alerting, et cetera, so that we could provide some good operational ability for Kafka. This in turn surfaced a variety of challenges with operating Kafka at scale. So today, we'll be talking about 3 of them. And in doing so, we'll go over some of the symptoms and observed behaviors, and then we'll dive into some inner workings of Kafka and how things work. And then we'll resurface and talk about basically the takeaways and some of the fixes. And we'll do this for each case. So starting with the first challenge we faced in production, let's take a look at some of the observed behaviors. So first, users were exceeding their produced quotas for long periods of time. Second, brokers were crashing and being restarted on a regular basis. And to make matters worse, we were seeing network threads getting null pointer exceptions all over the place. Okay, so with these 3 in mind, just to make things a little more simpler, I'll tell you The key insight here was with quotas. So for a little bit of context, at Heroku, we leverage Kafka's internal quota implementation. And the implementation of this has a traffic shaping mechanism, which it favors over a traffic policing mechanism. But why does it do this? Basically, the motivation is to avoid dropping messages, because Kafka is marketed as an at least once delivery system. So if you had a traffic policing mechanism, when users go over their quota, basically you would be just dropping the request and then you would be losing messages. So Kafka kind of wants to avoid that and maintain its marketed at least once guarantee with a star, because there are definitely caveats to that itself. So moving on, quotas are enforced on either the producer or the consumer side. In this particular case, we're concerned with only the producer side. So what does this look like for the end user? Well, from the user's perspective, messages are sent as a request, and it's essentially the payload to the request. The request gets sent over and taken care of by the broker, in which if the user happens to be over their quota, the broker will then extract the message from that request, write it to disk, and then put the request into some internal queue for the response to be sent back at some later time. Pretty much brokers ensure that users are then in compliance with the quota set in place. But this comes at a real cost, because it requires enough space on the broker to hold all of these queued requests. But the good thing is that Kafka does a pretty good job in that it makes sure it stores only what's necessary, and then it takes out what it can, and then makes sure that the GC can reclaim the on-heap memory. But actually, this didn't work as advertised at the time. It turns out that there was a bug. So if you take a look here, you can see that it says Java lang out-of-memory error, Java heap space. So I'm sure many of you have seen this type of error before. It's pretty straightforward. Again, if you haven't, let's take a look at some of the observed behaviors. Users were exceeding their quotas for long periods of time. Brokers were crashing and being restarted. No pointers everywhere. If you think about it a little bit, probably behaviors 2 and 3 on the bottom are just symptoms from the cause of number 1. Since Kafka does use this traffic shaping mechanism that queues things up, probably that was the culprit. So it looks like we're dealing with a heap-based out-of-memory problem here. So what do we do when dealing with heap-based out-of-memory problems? Well, first thing is let's capture a heap dump. Now, if you look to your right, there's a large retained heap. There's 26 million objects here. You look to the left, there's a crazy gobbledygook of stuff, objects that you might not know what they mean. So to better understand the context of this 26 million number and what the importance of it is, let's take a closer look at the produce request lifecycle in Kafka. So if we start at the entry point when a broker receives a request in Kafka APIs, it'll call this append records method. And this thing basically is what I said earlier. It'll just extract the message from the request, write it to disk immediately, and then it'll compute some delay with this callback to send the response at some later time, where if the user is over their quota or under some other conditions, then the request will get added to that queue, the internal queue, and then the response will be sent back later on. Finally, after that, it will clear all of the references to the underlying produce request. So it tries its best to clean up any potential heap-based growth problems. So this is great because at this point, messages would have already been extracted from the request. So if we held on to those references, then we would be unnecessarily taking up memory. But again, this wasn't entirely true because we weren't actually clearing out all of the underlying references to the produce requests on the broker, or Kafka wasn't. So first things first, we filed a JIRA. It's always good to get involved with the community, get extra feedback, seeing if someone else is working on a bug, or if you're entirely crazy. Turns out we weren't crazy because this thing actually ended up blocking the entire release in Kafka. So what did we do? We submitted a patch upstream. This patch got reviewed, merged in, and then it landed in Kafka 10.2. After that, we were able to release new versions or have it available to our users. They could opt in to upgrade on their own accords according to their own maintenance schedules and whatnot. But point is, it was pretty much available from that point on. So that was our first incident, heap base out of memory. Our second challenge we faced in production was a little bit different. If you take a look here, from these following observed behaviors, you'll see this time we were getting cascading failures of brokers. Brokers were being restarted, but then they weren't able to boot up successfully. But actually, some brokers booted up, but then all of a sudden would fail again, and this would happen on regular intervals, and it was quite deterministic. Like every n number of minutes, it would just keep failing. But it was bad because more and more brokers were failing continuously. Now, to preface, generally in distributed systems, as you all may know, you shouldn't expect services to be available 100% of the time. And this is especially true for us since we host all of our services on top of AWS. Still, though, it was pretty weird. We were far from 100% availability at this point. And if things trended, then we would be way farther from that. And way farther from our normal operating conditions of 4.5 nines. So this is pretty odd, why they were failing regularly and not able to restart. So, I mean, brokers crashing, systems crashing are pretty general, and those behaviors, they aren't necessarily very helpful if you're sitting there trying to think of, oh, what could be wrong? So to get a better understanding of what could be wrong, let's dig a little bit deeper into Kafka itself and look at these three things. First, we'll take a look at Kafka's HA model. Then we'll look at all of the work that needs to happen when a broker goes down. And then next, all of the work that a broker needs to do and the inter-broker communication that needs to happen when a broker comes up. So for Kafka's HA model, in Kafka, there's a concept of leaders and followers, where a leader will service read and write requests for all messages for a particular subset of the topic. Where followers, on the other hand, just continuously pull messages from their leaders. And these followers are also called replicas, but the point is basically they just have a consumer client that listens and pulls messages from the leaders. Now, leaders and followers live on brokers themselves, and a broker may have the role of a leader or follower, or both. The more important thing is let's consider the case where we have a user events topic. And this user events topic has 3 partitions. So for example, to illustrate the leader and follower concept, the broker on the left is leader for partition 0, or could be. The broker up top would be leader for partition 1, and this is for the user events topic. That's it. And then the broker on the right, the bottom right, would be lead for partition 2. Now, if we consider replication in here, as an example, again, the broker on the left for the user events topic, although it's leader for partition 0, it might be followers for partitions 1 and 2. Similarly, the broker on the top, although it's leader for partition 1, it might be followers for partition 0 and 2, and so on. And this is really just an example to illustrate the point because it really depends on the underlying mechanism in place to place these partitions across brokers. And it's really, there's defaults in place, but you can customize them as you wish. But more importantly, in essence, what we're trying to say here is Kafka tries to maintain balanced partition leadership among brokers. And where it fails, you should try to pick that up and then make sure that the load is evenly distributed across your cluster. With that said, brokers are generally lead for some subset of all partitions. So to illustrate this further, say, for example, we have 5 brokers, 1 topic, and 50 partitions. In this case, then, a broker will be leader for about 10 partitions on average, or 50 partitions divided by 5 brokers. In other words, a broker will process read and write requests for about 10 out of 50 partitions on average for this particular given topic. Now, if we consider replication factor being set to 3 on the topic, we'll have 2 additional copies of each partition. And ideally, these will be distributed across other brokers in the cluster. Although, again, depending on your placement strategy, they might not necessarily be that. That might not necessarily be the case. So replication itself, though, is pull-based. Again, they're just normal consumer clients that just continuously pull messages from their leaders. But the more interesting thing is that each leader maintains something called an in-sync replica set, or ISR for short. And these ISRs represent all followers or replicas that are currently caught up to their leaders. And this is really important because leaders will evict replicas or followers out of the ISR if they lag behind or get stuck for whatever reason. And this is really important for when a broker fails over. This is essentially how Kafka achieves HA, because only followers in the ISR may be elected as a leader. And this is okay because as long as they're in the ISR, that guarantee, Kafka's saying that that's the guarantee that they're fully caught up to their leaders. So if the leader fails, all you have to do is re-elect the new leader by just picking the first follower in that list. And that list is just some in-memory array that it keeps track of. So that's Kafka's HA model. Now, in still thinking about this cascading crashing issue, let's dig a bit deeper and look into what happens when a broker goes down. So in Kafka, there's something called a controller. There's one active controller per Kafka cluster. And these things just manage states of partitions and replicas using state machines. And this is really neat because it basically allows the active controller to perform administrative tasks, such as determining which brokers are lead for partitions and transitioning states for various partitions in the cluster. Now, speaking about states, we are mostly today concerned with the partition state machine. And more specifically, we're concerned with the case where a partition transitions from the online partition state into the offline partition state. And this will generally happen for many partitions at once. Why? Because remember, a broker is generally lead for some subset of all partitions. So when a broker goes down, it's lead for like 10 out of 50 partitions. All 10 of those partitions would be considered offline or no longer be able to read or written from. So then it needs to transfer those partition leadership over to another live broker. But as for a broker failing, though, there are 2 different cases, as normal. There's your regular clean shutdown and your unclean shutdown case, where the clean shutdown case works pretty straightforward. Basically, the shutting down broker will initiate a controlled shutdown sequence. It'll send a request to the controller. The controller will see this request and then preemptively try to move partition leadership from that shutting down broker onto another live broker in the cluster. After that, it'll just send back a response to the shutting down broker in which it's then able to just continue on normally with its local shutdown tasks, like any cleanup of metadata, shutting down handlers and listeners and whatnot. Unclean shutdown, however, works a little bit differently because the broker won't necessarily be able to tell the controller, the active controller, that it's shutting down because it might have just disappeared. So to understand how this works, we have to jump a little bit ahead and look at what exactly a broker needs to do, or at least one of the things it needs to do when it comes up. So the most important thing is when a broker comes up, it registers itself in Zookeeper, and it does so by writing its broker ID and some metadata as an ephemeral Z node. And this is important because essentially when the broker dies, so does its Zookeeper session, because it won't be able to talk to Zookeeper anymore because it's gone. So when the Zookeeper session dies, the ephemeral Z node goes away. And the mechanism around this is the active controller will have listeners that listen for these types of events. So when the ephemeral Z node goes away, all of the partitions that the broker was responsible for or lead for will then be transitioned into the offline partition state. And then the controller just does this by writing metadata locally to a map. Once they're in the offline state, the controller will transition them back into the online state, but this time it will put them onto some other live broker in the cluster. So that's what happens when a broker goes down. So far it's kind of involved. There's lots of work that a broker needs to do. So let's keep going and look at what kind of work the broker has to do when it comes up. So there are 2 slides here. This is the first. Basically, I'm trying to illustrate the point that there's a ton of work that needs to happen. We just mentioned a second ago that it has to register itself in Zookeeper. That's pretty quick, but one of the larger things that it has to do is instantiate this log manager object. And this log manager object is very important to the broker. It has a lot of work to do. Basically, it takes all the partitions on disk and loads them up into memory when a broker boots up. So if you have many partitions on a broker, then still it has to load them all up completely. So again, moving on with the startup, after the broker loads all the partitions and does a bunch of other things, it then will just register itself in Zookeeper, and then it's considered fully started and operational and ready to process read and write requests in the cluster. The major key here is that this is a lot of work that a broker needs to do on a failover. And this is a ton of work that needs to happen when restarts happen. So essentially, work is then a function of the number of partitions on a broker. More partitions means more work. And more work means more time required for brokers to recover when they boot up or when they fail and boot up. Now recall that some of our clusters have thousands of partitions per broker. So you can imagine that this could take a while. And unfortunately, at the time, our automation didn't consider this. You see, our automation would restart brokers just fine. And given the fact that recovery would take sometimes a little bit longer than expected, our automation would then see that, alert, time out the broker, and then restart it. And this would keep happening to more and more brokers in the cluster over and over again. So essentially, you could say our automation was a little too aggressive. So to fix this, we introduced a recovery state into our automation's own state machine, where when sitting in this state, the broker will essentially allow itself enough time to recover, in which this time we had additional monitoring and alerting around the situation where recovery takes unusually long. But this time, when it does happen, then we page a human rather than attempting automatic remediation. So the biggest insight here is sometimes you can quickly detect a problem or an anomaly and you can act on it just as fast. But that might not necessarily be the right thing to do, depending on your setup and depending on the variables at play. So in this case, we were seeing a legitimate case where recovery would take longer on certain clusters that had thousands of partitions per broker. But our automation would just go ahead and think that it's stalled from booting up for some reason and restart it. So there's definitely a trade-off to be had there and something to consider in general for systems like this. So that was our second incident in production. Our third and most recent incident was a lot more non-deterministic in nature, as you can see from the following behaviors. So everything was great. Everything was fine. After long periods of stability, things started failing all of a sudden. Brokers were crashing at various stages of the boot up process this time. So they would crash, it would be rebooted by our automation successfully, but then you couldn't really time at what point the brokers would start crashing. And to make matters worse, we were seeing under-replicated partitions grow uncontrollably and tons and tons of request timeouts happening. So I will point out here that the third symptom on the bottom is not necessarily a huge symptom relating to this, but it's really portraying the fact that under-replicated partitions is a big deal. Because what does this mean? It's basically saying there are followers or replicas in the cluster that aren't able to keep up with their leaders. They aren't able to keep up with the writes. So if replication isn't happening, then remember the leaders will evict their followers out of the ISR. And if that keeps happening, then that list, that array, will keep shrinking. And as that shrinks, then the likelihood of you losing data becomes much more greater. Essentially, we were under the clock, and we basically had to fix this as fast as possible, otherwise we would start losing data. So with that said, I would like to point out that this time our automation was not interfering. We had tons and tons more monitoring and alerting around this case, so that was not a thing. But remember that brokers do have to load all of their partitions when they boot up. And this makes sense to think about because the brokers were crashing, and as they boot up, one of the things they have to do is load all this stuff. But that's all that we can have so far, because we don't really know what it means to load a partition. So let's dive in. A partition is sometimes called a log, and this partition or log consists of many different log segments. And these log segments are actual files on disk, and they're created according to some frequency of when the log should be rolled, and that can be by or configured by time or size. So as an example here, not fully pictured, if you have a partition or a log that's rolled every 3 hours, then you would have 8 log segments per day. The biggest thing here is, in aggregate, this amounts to many files on disk. And remember that we have thousands of partitions per broker. So you can imagine that that is a ton of file descriptors, because the log segments have files, they're actual files, and files need file descriptors, so that could be a lot. And again, especially because these partitions or each log segment have to be read and completely load from disk and into memory when brokers boot up. Otherwise, during normal operation, Kafka does try to maintain file descriptors only for the active log segments. And then the deviation there just comes from when logs are being rolled or partitions are being rolled, where it'll temporarily hold on to file descriptors for old log segments. So with all that in mind, let's take a look at the service's operational logs. And by log this time, I just mean something that you would normally see in like a Splunk or a Sumo Logic. So to confirm our suspicion, it appears we are looking to be correct so far, in that it says there are too many open files in the system. So if we cross-reference that with the system itself, with procsys and then file.nr, you'll see that we are completely maxing out on our file descriptors. So to fix this, you'll have to examine the syscontrol along with the limits.conf and basically bump the number so that you have enough for the process while maintaining a sufficiently large enough buffer for the rest of the system. Great, but that's pretty hand-wavy still, so let's consider a rule of thumb. So we've done tons and tons of testing, and we found that on average it takes about 1.5 file descriptors per log segment. And this is because log segments do have 3 actual files on disk as of 10.2, not 0.11 anymore. In any case, the files are the data, the index, and the time index files. But why is it 1.5? Because remember that Kafka tries to maintain file descriptors only for the active segments, where the difference just comes from when logs are being rolled. But more importantly, you need to consider the number of inputs that are involved so that you can calculate a number for your Kafka cluster. And this is a number that's applied per broker. So essentially, you want to consider your partition replicas or your effective partitions. And you do this by taking the number of topics times the number of partitions and the replication factor. And keep in mind that replication factor and topic and partitions are configurable per topic, so you might have to be careful there. But in any case, in the simple case, you take those, you divide them by the number of brokers. After that, you have to consider your segments per partition replicas. And you do that just by taking the retention time and then dividing that by your log rolling configuration, in this case, log roll hours. Then you take those two resultants, multiply them together, and multiply them again by an additional buffer, in this case, 1.5. Cool. So we did that, and it did nothing. Our brokers were still not able to boot up. Not yet, anyhow. So looking back at the behaviors, long periods of stability, suddenly crashing, being rebooted, crashing again non-deterministically, and we were against the clock still. Taking a closer look at the operational logs, we see that there were 3 different errors, 3 important ones at least. So in a replica fetcher thread on a fetch, we saw Kafka storage exception, IO exception, and append to log. And this happens when a message is trying to be written to disk. Then, in a request handler on a broadcast metadata request, IO exception map failed. Okay. Finally, in a Kafka server starter thread, fatal error during startup. Prepare to shut down. Another IO exception map failed. Okay, so with these map faileds everywhere, could this be another out-of-memory problem? Or worse, could this be another memory leak? Well, you see, the odd thing was that brokers, when they were crashing, memory wasn't even saturated on these boxes. GC, we were getting acceptable GC evacuation pauses. Heap was okay. They were happening regularly. Cross-referencing that with the system memory yielded the same behavior, about 5 gigs out of 16 gigs available when they crash. So without thinking too deep into it, if you just look back at the logs, you'll see that it makes a reference to the file channel implementation in the map method. So if we dig into this method, into the C code, you'll see that Kafka tries to allocate memory-mapped byte buffers, or native memory. And this makes a ton of sense because Kafka internally heavily leverages native memory for many different operations. Knowing that, this was beginning to look like it wasn't a heap problem. And it's a real bummer here because this isn't readily apparent from the GC logs or heap dumps, so we can't use those tools to diagnose this problem further. Well, the good thing, though, is that there are tons of other ways to diagnose these types of problems, one of which we chose was to use or correlate various JMX metrics together. So in doing that, let's take a closer look at the logs to figure out what metrics we should start by looking at. Here we remember the file channel implementation. Notice that it comes from the request handler. And this seems like a reasonable place to start because the request handler receives requests from the outside world, from clients, and that's essentially the entry point to Kafka within a broker. So knowing that, using your favorite JVM visualizer, you basically take a look at some of the MBeans here. So here we looked at the Kafka network processor threads, and we wanted to look at the idle percentage across these threads. If you look closely, there are 3 different threads, 0, 1, and 2. And the idea here was maybe CPU was maxing out, maybe these threads were completely going insane, and there wasn't enough resources for them. That was BS because our threads were basically 100% idle across the board during the entire duration here. So that was highly suspect. I mean, we weren't sure if that was legit or not. So we wanted to take a look at some of the other metrics. Why? Because we wanted to rule out if there was a bug or not. And so we did this in conjunction with looking at the code. And in doing that, we decided to take a look at the request queue size, MBean. And the idea here was that maybe the requests are getting so backlogged and so backed up, and maybe the broker itself, when it serves a request, it just puts it onto the queue, very little CPU. And then there's some background async thread that processes it at some later time. But that turned out to be pointless as well because the backlog was 0 during the entire time. Not shown here is if you can actually click through and then see like a little graph of the historical values. And you just believe me that it was 0 across the entire, 0 for the entire duration. So after this, I mean, we got a little bit more confident, but still weren't sure. So after some more digging through the metrics and through some of the code, we basically arrived at the conclusion that there probably wasn't an error in the network part of the code. Okay, so now what? Well, remember, that Kafka heavily leverages native memory. And if you look closer at the metrics available by Kafka, we have the NIO, which Kafka uses pretty much everywhere. So with this, we wanted to take a look at the buffer pool mapped MBean and look at the counts. And all of this metrics observation was really useful because these metrics are exposed early on when the JVM boots up. So then it's readily accessible in case a broker does crash. So we were able to examine this, and we found that actually our memory mapped byte buffers were growing uncontrollably. So let's cross-reference that with the system. If you cat proc PID with maps, count them up, what do we get? A ton of memory maps, you may have guessed. So we'll hang on here, back up. So why would this cause the broker to fail? Because we had plenty of memory, disk, and other resources on these boxes for native memory. Actually, that was a lie. We didn't, because if you take a look here, if you take a look at the procsys VM max map count, we found that we had 65,535 maximum memory mapped regions available to us. Okay, so you're sitting there thinking 65K, great. I don't know if that means a lot or a little. What's the context here? Does this seem fine? Well, to understand it a little bit more, remember, we have many partitions per broker in some clusters. These partitions, otherwise called a log, have many log segments. These log segments have to be read and loaded completely when a broker boots up for each and every log segment. So knowing that, to top it off, and for additional context, we were running 64-bit JVMs, so there wasn't any weird integer overflow funny business going on here. So you can imagine that we indeed did not have enough memory mapped regions available to us. But still though, why does this matter? Because our brokers were surviving restarts many times before. And what's more weird is that we weren't able to reproduce this in our staging environment, which was essentially one-to-one with production. But there was a subtle difference. That's why I said essentially. And that difference was log rolling. So you see, we needed there to be enough traffic or retention to force enough logs to be rolled, which then would cause more log segments to be created, which then would require more memory mapped files when the broker boots up. Knowing that, we could see why this is why memory looked fine during a sudden crash. And this is why brokers would crash and recover and crash again in non-deterministic ways when they go to recover. So to fix this, you want to re-examine the syscontrol, and then you want to modify the VM max map count, where the idea is similar to before in that you have enough for the process and maintain some buffer for the rest of the system. Now keep in mind there are hard limits from the Linux kernel for what this is, and it's somewhere around 1 million. So definitely keep that in mind when you're modifying this file. So after doing that, our brokers were able to boot successfully once again. Unreplicated partitions started decreasing, and everybody was happy. Except us, because that was an unusually crazy amount of file descriptors and memory maps we needed for our brokers. So for completeness, we ran with this configuration a little while longer under heavy load in staging so that we could rule out the potential for any leak scenario around file descriptors and or memory maps. So we did that, and everything turned out to be fine. Everything was operating as normal, and there weren't any fires going on. So to wrap up, today we talked about 3 different things. We talked about Kafka and some of its internals. It's a pretty good piece of software in that it's flexible and it can satisfy tons and tons of use cases. But with this flexibility comes a real trade-off of there being many things to consider when operating this thing at scale. And as a final plug, at Heroku, we do offer Apache Kafka as a fully managed service, and we take care of all of these burdens, operational burdens and complexities for you, so you can just write your data pipelines. In our time running Kafka in production with hundreds of clusters over the last several years, we've encountered a variety of issues and challenges and incidents. Today, we only talked about 3 of them. We talked about how quotas work in Kafka internally and how we discovered a release blocking, heap-based, out-of-memory bug around quota management, and how we shipped a patch upstream that got merged in and landed in 10.2. Then we talked about how Kafka achieves HA through its replication protocol and mechanism, and a case where our automation was aggressively remediating brokers when they were legitimately trying to recover. And finally, we covered how partitions are implemented deep down in Kafka and all the state machines and everything else that are involved and all of the resources that are needed for when brokers boot up. Essentially, more partitions means more file descriptors and more memory mapped byte buffers required for brokers, especially when they're trying to boot up. So again, I'm Jeff Chow. You can reach me at jchow@heroku.com. I'll be happy to take questions after this talk, and we can talk about anything Kafka or streaming data infrastructure in general, and basically distributed systems as well. Thank you.
Thank you, Jeff. And I can take questions. If you raise your hand, I'll pass the mic to you.
Okay, thank you for the talk.
Sure.
This might be a dumb question. I don't know anything about the partition. So there were 50 messages in your example, and there were 3 partitions, 5 messages each partition. Why? Because I have lack of understanding of partition. Why partition is necessary? Can you just put all 50 messages in one?
Great. So the question was, how are messages routed among partitions within a topic? Can you, basically, if you have 3 partitions, would the messages be distributed evenly among those partitions, or could they be routed to 1 partition or 2 out of 3 partitions? The answer is yes, yes, and yes. It really depends on the hashing scheme or what kind of key you have in place. Basically, there's a function you pass through, and then it's up to you to choose Kafka's default, or you can supply your own, which basically dictates which partitions messages go into. So it's pretty flexible.
Other question.
I'm just wondering what happens if the controller crashes, because you mentioned it still saves some state in memory.
Mm-hmm.
So, yeah.
Great. So the question was, what happens when the controller crashes? Because this is a singleton, and in essence, it's a single point of failure in a Kafka cluster. So when the controller crashes, it's as of 10.2, and actually it still does. Basically, each broker has a controller object, and this controller object has different listeners, and it keeps track of different metrics in the JVM. So what happens is when a controller crashes, we are really saying the active controller, because there can only be one active controller at a time. When the active controller crashes, then the other brokers will see that, and then it'll pick the new active controller. And basically, there's code in there that looks at this particular controller metric. It's like the active controller count metric. And then that thing is either a 0 or a 1. If it's a 1, then that means it's the active controller. And if other controllers try to become the active controller, then they will be denied. And how does this happen? It just does that by locks in Zookeeper. Right. So the follow-up question was, I mentioned that the controller keeps the state. So is that state replicated to other brokers in the cluster? Because every broker has a controller object, although they might not be active. It is not replicated because all of that stuff is stored in Zookeeper. So when the active controller dies and another broker becomes the active controller, it will load up and cache all of that state from Zookeeper into memory. There was a question in the back, I think, too. Okay.
Okay. I just wanted to ask, you mentioned that you guys essentially have Kafka as a software, as a service, essentially over at Heroku. How much of a customization do you allow for the user, essentially, if, like, in terms of like log rotations, message sizes, all of these like maps and stuff like that? Like, as a user, can I go in and play around with it, or is it completely, essentially abstracted from me?
That's a good question. So the question was for the Heroku Kafka service, how much flexibility does a user have? Well, as a service provider, we want to prevent our users from shooting themselves in the foot as much as possible, because it's your cluster, but as my coworker says, your cluster, but we wear the pager. So we take care of it for you. But to answer your question more concretely, I don't remember offhand how many things you can configure, but there are quite a few things, such as we expose JMX for you, so you can mess around with that. I think it's read-only, though. I don't think you're allowed to have write access to some of the metrics. You're definitely not able to modify max map counts and file descriptor stuff, because that's kernel-level stuff. And then things like replication factor, number of partitions, and a couple other Kafka level stuff you can modify, but a lot of things we like to keep transparent to you. But if we are always looking for feedback of what things we can modify. For instance, we were investigating log compaction ratios, which is a different concept in Kafka. But basically, there are some weird cases where log compaction might not work as you would expect. And if you're interested, we can talk about that a little bit later.
So along those lines, what about max message size? Do you guys have users that want to go beyond the default 1 megabyte?
That's a good question. So the question was max message size. I missed that, sorry. So Kafka by default does 1 megabyte everywhere. We stick with that, unfortunately, or fortunately, I don't know. Because the tricky thing is when you modify max message size, you have to consider that you have to change it on the broker and the producer and the consumer as well. Otherwise, you might get unexpected behavior. So we've seen a couple tickets requesting some of that, something around that type of feature. And definitely we're aware of that. So as things progress more, we might even consider exposing that in some way. But for now, it's 1 megabyte across the board.
Cool, thank you.
Yep.
Also, what's your tech stack for your monitoring?
The tech stack for the monitor. So we have a lot of stuff built in-house. Unfortunately, our metrics pipeline is built in-house. Our logging pipeline is built in-house. Our basically request router is built in-house as well. But we do use some things like Librato and Splunk for log aggregation. And I think that's it. There are definitely some things that I'm missing, but for my day-to-day, those are the things that I would use.
Can you comment on the need to configure Zookeeper to support large numbers of file descriptors or anything like that?
Yeah, so for Zookeeper, so the question was, what kind of things should you be configuring for Zookeeper to catch these odd corner cases? Basically, Zookeeper would be the same. We don't have a rule of thumb for the number of file descriptors or memory map files that you would need for Zookeeper. But the idea is the same. You can kind of measure that and see, and then provide some buffer between the process and the system. But the thing with Zookeeper, though, I will say that you should, if you aren't monitoring the following, you should monitor them. You should be monitoring your fsync times for sure, and then your Zookeeper request times as well. And then that's kind of like your smoking gun of, is Zookeeper performing badly? But from some of these configurations, I said 50,000 partitions. That basically is, you can do the math. There's like, depending on the number of brokers, that's thousands and handful of thousands of partitions per broker. Zookeeper appeared to be fine, even till then. And why? Because the later versions of Kafka, we're kind of getting rid of the hard dependencies on Zookeeper. So starting with I think it was maybe last year or a year and a half ago by now, basically the offsets from the consumers, they are no longer by default stored on Zookeeper. They're stored in Kafka on the brokers themselves, for example. Yeah.
Hey, so you mentioned you were using the Kafka quotas to deal with sort of like misbehaving producers. I was wondering, like, did you also consider sort of like a reactive kind of auto scaling approach to like varying traffic patterns? And if you did, like, you ran into sort of any challenges there?
Yeah, so the question was, since we use Kafka's quota implementation, have we considered just letting them go over their quotas and then adding like auto-scaling the number of brokers out? We have considered something like that, not necessarily for quotas, but in general. And for quotas, it works a little bit different because that might not necessarily help. If you have more brokers, that just means your partitions would be distributed among those brokers. So really, if you remember, partitions are the fundamental building blocks for parallelism within a topic. So it's not like you would get any more throughput, maybe a little bit because there's less load on a particular broker to serve these requests. But at the end of the day, it's about partitions. So then I would say, what if you have more partitions? Well, you would have more throughput, which means you would hit your quota much quicker. So it's kind of not very useful for that case. But as for quotas, well, why do we even use quotas to begin with? Well, and why did we push it so hard? And that's, again, that's basically our job as a service provider. You know, we got to catch all of these very odd corner cases and really push the limits of an individual broker to its max and kind of see what it can do. And from there, once you've solved that, you know that you can just scale it out because there's tons of literature and blog posts or whatever on that. Basically, you scale out the number of brokers, and then you reassign partitions, and then you're good to go.
Back to that Kafka as a service, I wanted to ask, like, how do you guys handle essentially version updates and like scaling essentially of the cluster? Because back at the time, it used to be pretty tough.
Yeah.
Essentially get around, like repartitioning, reallocation of the nodes and that kind of stuff. So do you have any strategies, or are you kind of just like, load balancing elsewhere and then like putting the load back on the original cluster after it has scaled up?
Yeah, so that's a pretty big question. The question was, how do we deal with rebalancing partitions? How do we deal with rebalancing partitions in the case where we scale out number of brokers or scale down? And what do you do when you're just like restarting brokers with version upgrades and breaking changes in that? So all of that is tied really deeply into our automation. And the way our automation works is we have a state machine, and there are state machines for different layers of abstraction of objects in our system. There might be like a cluster level abstraction, a service level abstraction, and a server level abstraction. So each of those have state machines, and then they'll transition asynchronously into various states. And it'll stay within a state as long as it's progressing. Otherwise, some alarm will sound, and then it'll either page or attempt automatic remediation. So as far as balancing partition goes, there's two types. One is balancing partition leadership, and that happens when, say, you have a static number of brokers and a leader goes down. You need to move partitions somewhere else so you can service read and write requests. So we have that, again, our automation will see that event, and then it will move partition leadership over one by one. Similarly, when we add a new broker and we want to reassign partitions, like balance the load across brokers, we will do them one by one as well. Why one by one instead of just all of them at once? Or there's like a huge debate and discussion on mailing lists that if you do them all at once, that there's this huge issue. Personally, we haven't seen this problem, or not, I don't think there's hard evidence on that right now. But the biggest thing is to err on the side of caution. And if you can just do them one by one as fast as you can, so that your downtime is as minimal as you can, then that's okay. I don't really know offhand, but it's nothing terrible. I would say it's on the order of seconds in a lot of cases. And I say seconds because it depends on the type of failure and what do you mean by downtime. Because there are cases where the broker goes down and you need to reassign all these partition leaderships. But what if the broker that went down is also a controller? Then it has to transfer additional metadata up and do all these inter-broker communications. But all in all, when a broker is down, you can still service read and write requests as long as there's partition leadership elsewhere. And that's really because of Kafka's ISR mechanism. Yeah. Right, so the question was, how do you grow a cluster? And what do you do with offsets? So basically, when you grow a cluster, the consumers maintain their own offsets, and then if the partition is no longer available, it'll throw like an error or a warning, and then it'll be up to the client to kind of reassume the metadata from the brokers. And then that's pretty much it. But basically what happened, the mechanism around that is like you add a cluster or you add a broker, you wait for it to stabilize. Once it's up, you call the Kafka's, the internal tooling, the partition replicas reassignment tool. And then you wait for that to stabilize. And then its replica fetchers come up and then they're able to operate normally. Yeah. Yeah, I mean, it's pretty straightforward. You just call that tool and then you're good to go.
Any question on the back? This is the last one. Nope. Thank you, Jeff.
All right,
It's
thanks.
Great talk. So while you're set it up, so let me introduce the second speaker. So the second speaker is going to talk about the hierarchical memory, hierarchical temporary memory model for real-time analytics, real-time streaming. Sorry. So Yue Cui is a research staff at Numeta. Sorry. So he's interested in areas AI, computer neuroscience, and computer vision and machine learning. So welcome.
Thank you. Thank you, Chester, for the invitation and for the nice introduction. Today, I'm going to share some of the research we did at Numeta, and my title of the talk is What the Brain Tells Us About the Future of Streaming Analytics. So this will be a talk on the algorithm level for streaming analytics rather than infrastructure. So before I get started, this is just a brief history about Numeta in case you're curious about us. So Numeta has been around for a while. It is founded by Jeff Hawkins in 2005, who is also the founder for Palm and Handspring, as well as the Ralph Center for Theoretical Neuroscience. So we have roughly 3 generations of algorithms. The first one is focused on hierarchy and solving vision problems. It's using a neural network model that's very similar to nowadays convolutional neural network. And starting from around 2010, we started our second generation of algorithm. We call it the cortical learning algorithm, and starts to use a notion of sparse representation, continuous learning, and temporal inference. This is what I'm going to focus on today, and it's pretty relevant for streaming analytics. And we also decided to open source all our algorithm around 2013. We have a pretty active open source community called NewPick. And at the same time, we develop a number of demo applications to demonstrate what you can do with the technique. And the third generation of the algorithm focuses on sensory motor inference, so it's no longer passively data analytics, but rather it can also generate behavior to achieve certain goals. So we are pretty unusual in the group of machine learning and artificial intelligence companies in the sense that we are taking a very different approach. So instead of trying to solve a specific problem, the goal of Numeta is to discover the operating principles of the brain, and then secondarily to develop and create technologies based on those same principles. So we learn a lot from neuroscience, and in our data research, a lot of the theory development is constrained by neuroscience researches. And at the same time, we also develop demo applications and technologies that can be used for application domains like anomaly detection, temporal prediction for streaming data analysis, natural language processing, and so on. And as I said, we have open source community, and we also publish academia papers. And we also license our algorithm to other companies who can build actual applications around it. And the name of our algorithm is called HTM, which is short for hierarchical temporal memory. So those 3 words are the 3 principles we believe is important for the intelligence in the brain. So today I'm going to focus on real-time streaming analytics. So over the years, we have learned a lot from the brain, and it seems that many of the principles we learned there also are extremely applicable to the problem of streaming analytics. I will explain why that is the case and what we can do about it and what we can learn from it. So here is an example of one of the interactions we had with e-commerce company. So this is an example of traditional data analytics, which is not streaming. They have a data analytics team, and the goal is to produce a revenue forecast each and every day. And the way to do it is to collect, each day they collect all the day's data, and they have a team of data scientists looking at the data, crunch the model, and then do typical machine learning practice like cross-validation and model training, fitting. And then early in the morning, they get a revenue report for the executive team, which can decide what to do about it. And this can give you a pretty accurate revenue forecast number. But the problem is, if you want to scale this up to the next level, for example, instead of having a single prediction every day, you want to be able to react rapidly to changes. For example, to generate prediction every 15 minutes. And instead of a single number that covers the whole company's revenue, maybe you want to track all product categories and different geographical locations. So, which means you may need to build different, use different models to deal with these things. So there are two problems. First, there is a data infrastructure problem. And from our perspective, it's also pretty challenging from a machine learning and algorithm perspective. So it's not clear what type of algorithm can deal with these fast changing data streams. Basically, what they have been using is a batch manual approach. You have a team of data scientists that look at the data stored somewhere, and then decide which algorithm to use and to build the models, and then get a prediction. But on the other hand, in the future, we have this streaming data coming in all the time, and which requires automated model creation and continuous learning from the data, because the statistics in the data can be changing very rapidly, which also requires being able to make predictions not in real time, not just after you collect a batch of data and then do your training. You need to be able to adapt your model continuously from the data stream. So the demand for such streaming data analytics has been growing very fast, partly due to the exponential growth in IoTs. Sensors and real-time data collection is driving an explosion of the streaming data, and it has many applications. Here I'm just showing you a few of them, such as monitoring the IT infrastructure, uncovering fraudulent transactions for financial companies, monitoring energy consumption, tracking vehicles, or real-time health monitoring. So what's often missing, so people talk about anomaly detections in all these cases, but what often is missing is, although detection is necessary, but sometimes what we really want is prevention. For example, for health monitoring, it's far more valuable to predict a heart attack from happening than to detect it after it actually occurs. So the timing is also a very important criteria to judge the performance of an anomaly detection algorithm. So here I'm just trying to set up the problem formally. Assuming you have a large number of sensors in your system, for each and every sensor you have a stream of measurements, and it can go infinitely back in time, and you can assume it will keep going in the future. This is the mentality of streaming. And the goal here is, assuming you are at a particular time point, given all the past input and the current input, and decide whether the behavior is anomalous, that's for anomaly detection, or maybe you want to, for predictions, you want to predict future values of this stream. And you have to do everything before the next input arrives to get real-time streaming analytics. That means you need to report decision, perform any model retraining, do bookkeeping, and everything before the next input arrives, which in case where the data stream has a very high velocity, this can be quite challenging for traditional machine learning, because you cannot retrain the, for example, convolution neural network at each input. And there are several important differences from the traditional machine learning setup. So first, you cannot look ahead into the future. And also, there is no obvious way to do training and testing cross-validation, because the data you collected back in the past may not apply anymore at this particular time point. And everything here must be done online. Also, the system has to be fully automated and ideally customized to each sensory stream. So we need to do something quite different and rethink about our approaches. So what we learned over the years is some of the principles we found in the brain actually applies to this problem quite well. And in the next part of my talk, I will describe an algorithm we developed called the HTM sequence memory that solves this continuous sequence learning and prediction problem. So this is just a very brief introduction of neuroscience. At Numenta, we study the neocortex, which is a very thin layer of cells at the top of our brain. It's about the size of a table napkin, and the thickness is about 3 millimeters. This is the organ that gives us intelligence, and it supports almost all the high-level cognitive functions. On a very high level, the brain is a very powerful streaming analytics engine. It gets continuous data streams from our peripheral sensors, like our eye, ear, and touch sensors embedded in our skins. And it outputs a continuous stream of motor control, motor commands to generate the behavior in order to achieve some goals. So how does the brain do this? Well, neuroscientists have discovered a lot about how the brain works. Here, I'm going to focus on 4 properties that are particularly relevant for streaming data analytics. So first, the brain is organized into a hierarchy of nearly identical regions. So if you look under the microscope, you'll see something like this. It looks pretty complex, but the thing is, it's highly stereotypical, and it's the same structure, same neural circuit across the cortex. So regardless of whether you are doing visual recognition, speech recognition, or maybe generating motor behavior, it's the same neural circuit analyzes all the perception and behavior. So which suggests there is a universal algorithm at play here. And second, we start to learn how neurons represent information. So this is, if you look at under the microscope, the neural activity you see on top of the brain. So what you see here is that neurons represent the information with very sparse and distributed representations. And sparse just means at any time, only a very small fraction of the neurons are active, are responding to the sensory input. And distributed means any particular input is collectively represented by a set of neurons, such that if any particular neuron fails, let's say there's a cell death, so the entire system will not fail. So we call this SDRs, or sparse distributed representations. So this is the data structure that underlies all the algorithm we developed at Numenta. And thirdly, every cortical region has to deal with temporal sequences. And the ability to recognize and predict and generate sequences is critical to almost every function of the brain. So if you look at individual neurons in the cortex, most of the inputs to a neuron is coming from other neurons in the same area, and it's dealing with transitions of activities in the local population. So we think about it as doing sequence learning and sequence memory. So the third principle is sequence learning. And finally, all of this has to occur continuously. So we wake up every day and we don't do batch learning. We just start to open our eye and do streaming analytics and learn from the statistics of the data. So it has to happen in an automated and a continuous way. So those 4 principles, universal algorithm, universal data structure, sequence learning, and continuous learning. So those are exactly the same principles we need for streaming data analytics. So in the next part, I will describe a specific implementation for an algorithm for sequence learning. I'll start with a neural model. The vast majority of artificial neural networks use neural models like this. It's known by different names, typically like perceptron or the integrate and fire neurons. Basic idea is a neuron performs a weighted summation of all the inputs at the cell body, and the output of the cell depends on the integrated input via some nonlinear function, a sigmoid function or rectified linear function. And learning occurs by modifying the weights of these synapses. But from a biological perspective, this looks nothing like a real neuron in the brain, which looks like this. So there are several differences. First, you can see that the neuron has many dendritic, we call it dendritic branches, like a tree-like structure. And each individual branch is an independent computing unit. Basically, each dendritic branch can do its own computation, can recognize a pattern on that branch and decide whether to become active. And only the part that's near the cell body, labeled in the green area here, is operating like a integrated fire or perceptron-like neuron, whereas the vast majority of the input, 90% of the input, they target onto these distal branches, and the effect of activating one of the branches is not to generating an output of the neuron, but rather to prime the cell. We call it to depolarize the cell into a depolarized state and make it ready to fire when the actual input, feed-forward input comes in. So there are two sets of inputs, functionally different inputs targeting onto the cell. We have the feed-forward input targeting in the proximal zone near the cell body. That's defining which sensory input the cell is going to be responding to. And we also have many dendritic, hundreds of branches, and each one is deciding a context for that particular input. So we can have, for example, the same note, but in different melodies, they mean different things. The same word in different sentences, they mean different things. So this is, in our model, is due to the distal dendritic segments for context detection. So we model the biological neuron with what's called an HTM neuron. It has thousands of synapses and hundreds of dendritic segments. And each one of the segments is active computing units, and it can recognize unique patterns on it. And learning occurs not just by modifying weights of synapses, but also by modeling the growth and death of synapses. So here is a network of HTM neurons. So in this case, we put the neurons in a two-dimensional network. Each column, they share the same feed-forward receptive field. So they are detecting the same sensory pattern in the data. So the streaming data will come from the bottom up. And across the mini columns, there are lateral connections that makes the neuron sensitive to different contexts. So in this case, I'm going to show you the state of the network at two scenarios. One is with prediction, one is without prediction. So this is no prediction, like the first note in a melody or the first word in a sentence. You don't have any context yet. So the effect for a feed-forward input in the network is to drive a sparse set of columns to become active. And in this case, all cells in the same column will become active. So here I'm showing time t minus 1 and time t. And in the second scenario, assuming that we are in the middle of a melody, so when the feed-forward input comes in, a set of cells in those columns will also get lateral connections from other cells in maybe other mini columns. So those represent transitions of sensory input. And the effect of that transition is a subset of the cells will be depolarized via these lateral connections, making them closer to the activation threshold. And when the actual input comes in, only those depolarized cells will become active. So this is due to we have two inhibition systems in the network. One is operating within each mini column. The other is operating across the columns. And functionally, we have two separate sparse representations at this state of the network. One is at the column level, it's representing the current sensory input, current data in the data stream. And the other one is at the individual cell level within the mini columns, which represents the specific context for that input. So why do we need this dual sparse representation? Well, if you think about sequence learning, to be able to predict what's going to occur next, you need to know more than just the current input, but also some of the past inputs, the history context, for you to be able to predict the next thing. So here is a very simple toy example. Assuming you have two sequences, ABCD versus XBCY, and in order to predict what's going to occur after the element C, the third element in the sequence, you need to know the beginning of the sequence. So you need to know more than the local context, maybe several steps back into the past. Here I'm showing you the state of the network before learning. and time goes from left to the right. And before learning, each input causes a sparse set of columns to become active. And after learning, if you repeat the sequence many times, there will be lateral connections forming across the mini columns from a set of A cells to a set of B cells, and from a set of B cells to a set of C cells. So it's a transition of activity. In the end, you have the same set of columns containing active cells, but within those columns, only a sparse set of cells will become active. And those represent the context for the sequence. Here I label it as B prime and B double prime, which means a B input in the ABCD sequence versus a B input in the XBCY sequence. And this prediction can propagate forward in time, such that at each time point, if you just look at which set of columns containing predicted cells, you can decode the next input in the sequence. So this model has several interesting computational properties. For example, I just showed you it can handle higher order sequences, like the ABCD, XBCY example. And the learning rule here is just using typical Hebbian learning, wire together. And it's fully local and unsupervised, and it can be done in an online fashion. It has also a few other interesting properties, such as it's very robust to noise and to system faults. After learning, even if I kill 40% of the cells from the network, it can still function properly and make correct predictions. Also, it has a very high capacity because we use a sparse distributed code. The network of thousands of neurons can represent a very large number of sequences. Here are a few example use cases. In this case, I'm creating a large number of sequences in the same spirit as ABCD versus XBCY. So all the sequences have a shared subsequence, but the starting and the ending element are different, which is the context. And they are presented to the network in a continuous fashion, which is separated by some noise element. And the task is to predict the ending element of each sequence. And also, after it learns the sequence, adapted to it, get perfect prediction accuracy, I switch to a different set of sequences which contradicts the original set. This is to test the ability of the network to adapt to new statistics in the data. And in this case, I'm plotting the prediction accuracy of HTM versus RSTM in yellow and green here, which RSTM is a very popular recurrent neural network that can also do sequence learning, as well as an extreme learning machine. It's a feed-forward neural network model. And accuracy is plotting as a function of number of elements seen in this data stream. And in this case, HTM and RSTM with a large enough buffer can both handle the task perfectly. But RSTM here is using a batch learning paradigm, which is retrained regularly as the orange vertical lines here. And after the network gets stable performance, I switch to a new set of sequences, which is different from the original one. And initially, the performance will all drop down sharply. But for HTM, it can recover fairly fast compared to the other models. This is due to the use of a continuous Hebbian learning rule rather than a batch training paradigm. Also, at this time point, I can kill a fraction of the cells in the network and see what happens. So here I'm showing you the accuracy after the cell death, but without any retraining. So for HTM, up to 30% cell death has no impact on the performance at all. But for traditional artificial neural networks, typically the accuracy will go down immediately as you're starting to remove cells from the network. So we have taken this algorithm and created an engine called HTM engine for streaming data analytics. The engine takes a data stream and encode it into this sparse and distributed representations. And the core algorithm is a neural network that's agnostic about the nature of the data, and just say a transition of these sparse vectors. And at any time point, we can use a simple classifier to decode the activation state of the network to either a prediction value, a classification label, or anomaly score, for example. we applied it to a number of real-world tasks, and this is one of them to predict the number of demand for taxi in New York City. So this is an example data stream in this data set. We have a aggregated passenger count in 30 minutes window. This is over a week time. So as you can see, there is a daily temporal pattern as well as a weekly pattern. So the pattern on Sunday is different from that on Monday, for example. And the goal is to predict taxi demand in the future, 2 hours ahead of time. So here I'm showing the prediction error of HTM versus other algorithms. So we compared HTM with statistical methods such as ARIMA, feed-forward neural network, and recurrent neural network like LSTM, echo state network. So HTM and LSTM are having the best performance overall. But if you just look at those two models and plot the error as a function of time, you can see that. So here is after I manually inject a new pattern into the data set and trying to judge how fast different models can adapt to that change. So initially, after you introduce a new pattern, the performance will all become worse. But for HTM, a continuous learning algorithm, it can adapt fairly quickly to the data set, to the new pattern. Whereas using a batch training paradigm, you need to wait much longer before you can pick up a new pattern in the data set. So I have shown you the computational properties of HTM and some of its use cases on real-world streaming prediction problems. At Numenta, we also tried hard to benchmark the system and understand it more comprehensively. But it turns out that there's almost no good benchmark out there for streaming analytics. So we create our own benchmark for anomaly detection in this case. So the benchmark has two components. It has a large number of streaming data sets. And for each data set, we have a we have a human labeled. You have human labels for the anomalies. So this is an example data set. In this case, it's a machine temperature from a machine temperature sensor in a large industrial machine. And there are 3 anomalies, according to the engineers. And some of them are fairly easy. Like the first one is an obvious outlier. But the second one is not that easy to catch, that high frequency oscillation. But that's actually an early indicator for the third one, which is an actual failure of the machine. The second component of the benchmark is a custom scoring system, which not only we rank algorithm not only based on whether they detect anomalies, but also on how early it can detect the anomaly. If two algorithms both detect the anomalies, the ones that detect earlier will be giving a higher score. There are a lot of numbers here. This is the performance of different algorithms on this benchmark. So 100 will be perfect and 0 will be nothing. So in this case, we are comparing a handful of different algorithms, and HTM is doing fairly well. The reason for this is not just because HTM can catch every anomaly, but also because, so here I'm showing you one anomalies. The first label is HTM, and as you can see that it often can detect anomalies much earlier than the other competing method. And this is one of the important reasons for it to have a higher anomalies, a higher performance on this benchmark. So in the last part of my talk, I will talk about some applications we have built. So over the years, we have built a number of different demo applications. So this is mainly to demonstrate what you can do with algorithm. We didn't do it for commercial purposes. So they are all using the same HTM engine for streaming analytics, but in different problem domains. For example, we have applications to detect server anomalies for data centers, human behavior anomaly based on the keyboard inputs, financial stock anomalies, social media anomalies based on Twitter data, and the last one is for geospatial tracking anomalies. And they all share the same the same HTM algorithm with the same parameters. The only difference is we have different data inputs and different encoders adapted to different data. For example, for GPS data, we have a different encoder than for the IT data. This is an example for the detecting anomalies in IT infrastructure. We had a partner company that actually built a product using the technique. So here I'm showing you 3 different types of anomalies. The first one is monitoring CPU utilization on AWS. As you can see, here is a very predictable stream, and suddenly the CPU utilization increases. And initially, it will report an anomaly, but over time, it can adjust and learn the new norm, so it won't keep saying it's anomalous due to the ability to learn quickly from the data. The second one is fairly unpredictable data, but somehow it also gets the anomaly at the right place. And the third one is a temporal anomaly because the indicator for the anomaly is a high frequency oscillation that's in the time domain. This is the second example is we take the same algorithm and apply it for geospatial tracking anomaly detection. So we have a special coordinate encoder that turns GPS coordinates and velocity into a sparse representation. And then we feed the stream of SDRs into the same core algorithm and to detect geospatial anomaly. So this is the performance behavior of the algorithm over multiple days. So this is a commute route for one of my co-workers from Cupertino to Rev City, I believe. So the red means anomalous and green means normal. So on the first day, this is the first time the algorithm sees this stream of GPS coordinates. Everything is new, is anomalous. But after a few days, after a few repetitions, the algorithm is able to learn the sequence of GPS coordinates. And this is showing on the 5th day, it almost have the entire route in green, means it seems normal to the algorithm. And after it learns the GPS route, let's say, for example, you take a exit. It's not the normal exit you took, and this will be labeled as a position anomaly. If you make a U-turn in the middle of the road, this is something you have never done before. It will be labeled as a direction anomaly. Also, this is where he speed up in downtown Rev City, which he normally don't do that. This will also be labeled as a speed anomaly. So those are different types of anomalies. We don't train the algorithm to detect those things specifically. Just from the statistics of the data and the structure of the data, it can label them, it can detect them using the same core algorithm. Sure. It can still remember the old path. As long as it doesn't contradict the new one, it won't be labeled as an anomaly. Yeah. But after a while, it will forget. So those are parameters you can tweak with, like how far it learns new things and versus how fast it forgets the things it has learned. This is just to wrap up. I think we're still really early in this very initial stage of dealing with streaming data analytics. And I think the high velocity streaming data is the future of, it's a very important use case for intelligent applications. And it requires new algorithms that can deal with high velocity sensory streams with rapidly changing statistics, as well as the ability to learn continuously and automatically from the data stream. And the problem with existing batch algorithm is just lacks of flexibility and to deal with these fast changing data streams. So the HTM sequence memory is a proof that an algorithm based on the cortical principles can deal with this problem. I showed we can automatically create a large number of models and dealing with different types of data streams, and can learn continuously from the data and can model sophisticated temporal data streams. and we can demonstrate it working with several demo applications today. And just a few resources for that IT anomaly detection demo. We have a partner company working on that. We also have a HTM studio, which is a easy way for you to start with the algorithm without coding. And all the demo applications and the core algorithm are open source on GitHub. And this is my contact info. And I'm ready to take questions. Yes. Mm-hmm. Yeah. Yeah. Well, what do you mean by I don't have any data? I do have a data stream. It's a continuous data stream.
So in typically, right, in a machine learning thing, you build a model from
Yes.
Previous data so you train the model, right?
Yes.
And then you apply the model to a real world
Yeah.
problem.
So there's training and testing phase.
Here you're saying that it's not there. It's so
training. So here at every input, I do training and I do inference at the same time. I just don't separate the two. So the network is continuously learning. It continuously giving you an output.
Okay, so my question is, in streaming, right, in data streaming,
yeah.
What is the best data representation for this problem?
So all we need is, for this to work, is an encoder that turns whatever data you have into a meaningful sparse representation. What is meaningful is it has to share, so similar inputs in your data needs to have a high overlap in the sparse representation. So that's all we need to know. For example, for the GPS, nearby locations will be encoded into sparse vectors that have a lot of overlapping active bits.
So you provide this encoder also as part of your algorithm? Do you provide the encoder, or do we have to write the encoder for this?
Yes.
We have to write an encoder.
Yeah, we have a list of encoders on our repo. Dealing with different, for example, you may have a scalar value and GPS, spatial positions, and daytime encoder, and there are a number of different options.
So, which means when I'm feeding data to the encoder, I must format the data so that encoder understands the data that I'm sending in, right? I must format the data.
Yes. So there are already a list of existing encoders you can just use directly. If you are feeding a new type of data we have never dealt with before, you need to develop your own encoder to translate the data into the sparse format.
Hey, thanks for the presentation. So I have a question about the applicability of the algorithm. So far, all the examples you've given seems like there's a certain continuity back in the data sets. How well does the model work with non-continuous data? For example, if you sample from some a certain distribution and there's no continuity in the data.
So I would say the model, so this model is primarily developed to deal with continuous streaming data, where you have some repeatability in the data, like a daily pattern or weekly pattern. So we are looking for temporal patterns in the data. So if it's not a temporal problem, it's not a good option to use the model. Yeah, it's not learning a spatial distribution of the data.
Other questions?
Thanks for sharing this. And you have a comparison between HTM and LSTM. I'd like to ask how the HTM is different than if you do a batch size of 1 of LSTM. Every time you receive a data, you can do something, or you even loop back the T label to T+1, so you can.
So for LSTM, you need to have a batch size, right? You need to retrain the network regularly, right?
Yes.
And that batch size is a limiting factor here because it limits how well you can. It's a trade-off between flexibility and adaptation to fast-changing statistics versus being able to handle like let's say you want to look for a really long temporal patterns, then you need a very long batch size, a big batch size for LSTM to pick up that temporal pattern. So for LSTM, I'm trying to say that for LSTM, the batch is a limiting factor. Because if you have a really large batch, you can capture long-term dependencies, but you can't be very flexible and you can't adapt very quickly, right? Does that make sense?
Thank you.
Yeah.
So there's another way of doing this, which is I run more than one model at the same time in LSTM with sliding start windows.
Sure.
And then I can do any batch size, multiple batch sizes, and I have built-in ability to forget because each model starts at a different time point.
Yeah, if you.
And that's actually in Kafka is pretty easy to do.
Yeah, but then you have to train multiple models, and in this case, I'm just using one model.
But it'll work. This will work on anything, without assuming the temporality that you're assuming.
Using more computing resources, I guess.
Well, have you actually done proof that you actually use those computer resources?
So in our case, we can on the typical laptop we can do continuous learning, inference and learning for each input data with less than 10 millisecond time for HTM, and it actually can work in embedded systems. Whereas for LSTM, it's pretty hard to do that to deal with a very high velocity data stream.
Maybe define the anomaly. So let's say you had like weather patterns that were occurring every like 50 days, but with a high variance of like 30 days. Would it pick up any kind of anomaly each time it happened, or would it just always say this is always an anomaly?
If it happens regularly, it will not be an anomaly. So anomaly means something that's not predictable or it's not expected.
But I mean, like if it's somewhat regular with the average spacing between each event, but the amount that it varies from that average is very unpredictable, then is that regular or is that an anomaly?
You mean from whether the algorithm can pick it up or whether that should be defined as an anomaly?
Yeah, well, I guess both. Like, what would you say to both?
So from the algorithm perspective, I think if it happens regularly but it's not predictable, you are saying, because the latency is different.
Yeah, it varies.
It varies
from whatever you say the average is. Is that like a parameter that you tune maybe? Like,
no, I think it depends on how much data you have. I would guess it won't show up as an anomaly if you repeat it enough time. After a few repetitions, we'll learn it.
Okay.
Yeah.
Any other questions on the other side? More? Thank you very much, Dr. Trey.
Okay. Okay.
Thank you all for coming. We have another talk at the end of this month. It's by Uber, talking about the new open source project called Hoodie. So that's how to processing Hadoop big data in terms of dealing with the delete and update. So absurd. So that's going to be in Palo Alto. Okay, see you next time.